there is some, okay, and here's where the notation can get a little tricky if you're not thinking about it, okay? P is a collection of sets. So the elements of this collection are sets. Okay? And I use the word collection instead of set. It's just a synonym for set, right? But it just sounds a little, I mean, just to help you keep everything straight, right? I'll talk about a collection of sets as opposed to a set of sets. And that was one of the proposed solutions to all the problems that people found, you know, in terms of, you know, paradoxes and all that, was to sort of have hierarchies of you know, what's a set and so on, but that doesn't work either. So anyway, but I will use the word collection to help motivate and keep in mind what, you know, what this thing is, right? So there is some set A, an element of P. So right, this is a set element of this thing, which is a collection of sets, such that X is an element of A. And the second condition is that if A and B are sets in this collection, and A intersect B is not equal to the empty set, then, well, given what we just proved, what would we probably want to conclude here? Because we basically just proved that equivalence classes form a partition. So if they meet at all, then they have to be the same. Okay, so let's examine this definition a little bit. Basically what's happening here is you're starting with some bad marker and trying to draw a black set. So what this partition does, first of all, it says that everything in the set has to be in one of these partition elements. Okay? And then it says that these partition elements do not overlap. Do you see why it's called a partition then? Because a partition is something that chops up into pieces, like this, whatever that is, stick board, is partitioned, right? You got this, 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 and this, right? We'll forget about that, okay? And every part of this stick board thing is in one of these, okay? If we didn't have this set in here, but we were still considering the whole thing, that would not be a partition, because there'd be a bunch of stuff over here that was not in the partition somewhere. All right? And there's no intersection. Okay? That's what the second one says. If you pick up any two of them, if they are, so the contrapositive of this is if they are not equal, then they do not intersect. Okay? That's the contrapositive statement. So there you see that over there, right? So you take this set and you divide it, the entire thing up into non-overlapping pieces. We'll just leave a black piece in there, right? So then this. So how many elements are in that partition? 3. You can tell that without even knowing what the set is like, because remember, the elements of the partition are those sets. And there are 1, 2, 3 sets in that partition. So I've chopped this set up into non-overlapping pieces. And so a corollary of this statement here is that if X is a non-empty set with an equivalence relation, then the sets, the equivalence classes, of tilde form a partition. And one of your homework problems is to go in the other direction. So really, here's your partition again, right? How do you define an equivalence relation so that these are the equivalence classes of that equivalence relation? You say that two elements are equivalent if they happen to be in the same element of the partition. Now there are some details to work out. You have to show that that's an equivalence relation, and then you have to show that the equivalence classes of that equivalence relation are the original sets. Okay, so that problem is not inherently difficult, but there are a lot of steps and you need to make sure that you cover them all. And so given that homework exercise and this statement here, partitions and equivalence relations are logically equivalent ideas. Anytime you have an equivalence relation, the equivalence classes give you a partition. Anytime you have a partition, you can find an equivalence relation that determines that partition using its equivalence classes. Okay, so there, but usually you define first of all the equivalence relation, and there's some very important ones that we need to talk about. Actually, we'll start by talking about some unimportant ones. So first of all, we have the trivial equivalence relations on a non-empty set X. Okay, what's the most simple-minded thing you could think of? And there are two possibilities. Okay, they're equally simple-minded in some sense, right? But what's the simplest thing that you could say if you pick up two elements? All you know is you've got a set. So really, what are the possibilities?
They're equal to each other?
Or they're not. Okay, so that's one possibility. So X is related to Y if and only if X equals Y. Okay, why is that? I mean, let's just go through quickly. It's not really difficult to prove it's an equivalence relation. In fact, this is sort of the mother of all equivalence relations, equals. Okay, because X is always equal to X, right? And if X is equal to Y, then Y is equal to X. And if X is equal to Y and Y is equal to Z, that's the, that came up earlier, right? That's sort of built into the axioms that we use, right? Then X is, okay, so this is certainly an equivalence relation. And what is X bar for any X? What is the equivalence class of X? It's a set. Go through your mind. What set is it? It's just start with the definition, right? It's a set of all y such that what? And what does it mean for y to be related to x?
Y equals X.
Y equals x. So, what is the set?
X.
Yeah, set containing x. Okay? Which is, of course, totally uninteresting because now what is the set of all equivalence classes? It's just you pick up each thing in the set and you put it in its own little set. Okay? Doesn't really change anything. You're just putting brackets on there. There's a one-to-one correspondence between, right, between the set of all equivalence classes and the original set. Okay, so that's the first, excuse me, the first trivial one. And some kind of pollen in the air today. What about the other most simple-minded thing that you could do? And if you bring it up, it doesn't mean you're simple-minded. It means you're smart because you can think of the most simple-minded thing. And you can quote me on that. How about just say everything's equivalent to everything else? I said it was simple-minded, right? Okay, so, right? Let's check that this is an equivalence relation, okay? We're just saying that everything is equivalent to everything else. Okay, so what about reflexive? Well, yes, x is equivalent to x since, by definition. Because everything is equivalent, right? Okay, what about 2? If x is equivalent to y, then y is equivalent to x since everything is equivalent. So this is kind of the opposite of a vacuous hypothesis. This is a situation where the conclusion is always true, no matter what. Right? And if the conclusion is always true, then you're in good shape, right? Because always true. And 3, if x is related to y, and y is related to z, then x is related to z because everything is related to everything else. So again, the hypothesis doesn't even come into play here, right? The definition just defines everything to be equivalent to everything else. And so, what are the equivalence classes? We pick up any x, an element of x. What is x bar? It's the entire set. In other words, how many equivalence classes are there? 1. So you see why I called these the trivial cases, right? One case takes every element and puts it in its own little partition set, okay? All by itself. The other one takes everything and puts it in one partition set. And you can do this for any non-empty set. And whenever you can do something for every non-empty set, it's probably not interesting because it gives you no way to tell anything different between this set and that set. Okay? So that's why they're called trivial. They're pretty easy once you think of them, right? And they don't get you very far. Okay, let's do another example. Define, okay, so we'll say we're doing again all sets. So for non-empty sets A and B, say that A is equivalent to B means there is a bijection F from A to B. Okay? Let's check that this is an equivalence relation. A is equivalent to A for all sets A since, what's your favorite, by now I hope, bijection from A to itself? Well, A is not a function from A to itself, but what's the easiest function? We just got it last time, right? From a set to itself. Remember, it came into play. Identity. Identity function. Yep. See, the identity function is proving itself to be more and more useful, even though it's a simple-minded thing, right? Okay? So not all simple ideas are useless. What about symmetric? Okay, I've said it's an equivalence relation, so let's go ahead and start the proof. Suppose that A is related to B. What does that mean? There is a bijection F from A onto B. Who can tell me a bijection from B to A?
F inverse.
F inverse. Very good, right? We proved that the inverse of, and one of your exercises